Hi everybody. So in this video, we're going to look at calculating a probability using a binomial distribution. So we'll work through 4 questions, and if you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. So in our first question, we're told it is known that on average 1 coffee pod in 10 is defective, and 8 pods are selected, and the number of defective pods is denoted by Y. For part A, we've been asked to state 2 conditions needed to model Y by a binomial distribution. So the first condition is that the selections must be at random and independent of each other. So this means that for every one you select, it has no effect on the next one that you'll select. And the second condition is that the probability must remain fixed during these selections. So if you select 1 coffee pod and that changes the probability of selecting the next one, then the binomial distribution wouldn't be appropriate. But then we're told that assume that the binomial model is valid, and we've been asked to work out these probabilities. So we need to define our binomial model. So we're saying that Y is distributed binomially with 8 trials, and our probability of success of 1 coffee pod in 10 being defective would give us P as 0.1. And then we need to define the random variable Y. So I'll say that where Y is the number of defective coffee pods selected. And then to work out the probability of Y equaling 0, we can do this on our calculators. If we go to Home, and we'll choose Distribution, we want Binomial PD. Binomial CD we'll cover in the next video, but for this video, we're going to use Binomial PD. This is the probability distribution. We'll choose Variable. Then we need to define our value of X, and in this case, we're using 0. Our number of trials is 8, and the probability of success is this 0.1. We'll execute this, and the probability of selecting no defective coffee pods is 0.4305. Okay? Then for the next one, the probability of Y equaling 5. Well, if we are clear this, we'll change our value of X to 5, and we'll keep N and P the same, and then we get 0.0004. Okay? And then to work out the probability of Y being greater than or equal to 1. Well, if we look at the 8 trials, we can have 0 defective, 1, 2, 3, 4, 5, 6, 7, or 8 defective coffee pods. And what we want is at least 1, so 1 or more. Now it's certain in our 8 trials we'll have one of these events. So altogether, they must add up to make 1. So to work out the probability of Y being greater than or equal to 1, we can have it is certain, 1, minus the probability of Y equaling 0. If we take this 0 away, we get all the outcomes greater than or equal to 1. And we've already worked out Y equals 0, 1 minus 0.4305, which works out as 0.5695. Okay? Let's try another question. So in this question, we're told that during a medical trial, a new diagnostic test is used to detect a certain disease in patients, and the test is known to correctly identify a disease with a probability of 0.45, and each test result is independent of the others. The test is conducted on 15 different patients. We've been asked to determine the probability that out of the 15 patients tested, the test correctly identifies the disease in exactly 3 patients and in more than 1 patient. So do you want to try these questions yourself? You can pause the video and come back when you're ready. Okay, so I'll come back if you had a go. So because the probability remains fixed at 0.45, and the test results are independent of others, we can use the binomial distribution. So x is distributed binomially. We've got 15 trials and a probability of success of 0.45. And we need to define our random variable x. So we'll say that x is the random variable, the number of patients correctly identified. And then for part 1, to work out the probability of x equaling 3, we can go to home, we'll choose distribution, binomial PD, we want variable, and we'll change x to 3. The number of trials is 15, and the probability of success is 0.45. And we get 0.0318. Okay? And then for part 2, the probability of x being more than one patient, so greater than 1, well, if we've got the entire 15 trials, and it is certain that one of the outcomes will happen, the probability of x being greater than 1 will be 1 minus the probability of x equaling 0, which is less than 1, or the probability of x equaling 1. And we can work these two out on our calculators again. This time, if we go to list mode, I'll choose back, binomial PD, and I want list. We'll choose x as 0, and then x as 1. We'll execute that. We'll keep the 15 trials, the same probability of success, and then the probability of x equaling 0 is 0.00012. The probability of x equaling 1 will be 0.0015. So the probability of x being greater than 1 will be 1 minus, and we get 0.00162. We can work this out, and we get 0.9984 to 4dp. Okay? How did you get on with that? Let's try another question. So in this question, we're told that the probability that Jake's dog Max chooses to sleep in his kennel outside is 0.35, and Max's choice is independent from night to night. Part A, we've been asked to determine the probability that during a period of 2 weeks in winter, Max chooses to sleep in his kennel. For part 1, exactly 5 nights, and for part 2, exactly 8 nights. And then for part B, the period has changed to 3 weeks, and we want exactly 4 nights. So again, do you want to try this question yourself? Okay, so if we define our random variable, we'll say that y is distributed binomially. For part A, we've been given 2 weeks, so this will be 14 nights, and a probability of 0.35. So we want the probability that y is equal to 5. So if we enter this into our distribution, we'll go to home, we'll choose binomial PD, we'll choose variable, we'll set x is 5, 14 trials, and a probability of 0.35. And we get 0.2178. And then for part 2, the probability of y equaling 8, we'll calculate this. We'll change the 5 to an 8. We'll keep NMP the same, and we'll get 0.0510. Okay? And then for part B, now we've got a period of 3 weeks. So because n has changed, we need to define our new model. So I'll say W is now distributed binomially. We've got 3 weeks, so n is 21, and we've got the same probability. And we want the probability that W is exactly 4 So if we all clear this, we want x as 4, but we'll change n to 21. And we get 0.0593. Let's try one more question. So in our final question, we're told that a factory produces light bulbs, which are packaged in boxes, and the manufacturing process is such that on average, 5% of bulbs are defective, and each bulb is tested before being sold. 12 bulbs are selected at random. For part A, find the probability that exactly one bulb is defective. And then for part B, find the probability that at least 2 bulbs are defective. So do you want to try this last question? Okay, so I hope you did well with this. If we define our model, we'll say x is distributed binomially with a sample size of 12 and our probability of success as 0.05. And I'll define the random variable. So I'll say where x is the number of defective bulbs selected. Then for part A, we want the probability of x equaling 1. So we'll have x as 1, n as 12, and p as 0.05. And we get 0.3413. For part B, probability that at least 2 bulbs are defective. So probability that x is greater than or equal to 2. Well, out of the 12 trials, we want the probability that at least 2 are defective. So we can work this out as 1 minus the probability of x equaling 0, which is this outcome, or the probability of x equaling 1, which is this outcome. So we can go back to our calculator. I'll choose back. Now I'm going to choose list. We want x equals 0 and x equals 1. And then we want the same number of trials, the same probability. So then we've got 1 minus 0.5403 plus the 0.3412. We can work this out and we get 1 minus 0.8816, which is 0.1184. So this is the probability of x being greater than or equal to 2. Okay. Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe. And you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.